Hello everyone. So today I'm just gonna give you an overview on RNN. So what RNN is, RNN stands for recurrent neural networks, and so it's a type of neural network, unlike just like multi-layer perceptrons, convolutional neural networks. So what is an RNN and why do we need an RNN? So as I said, RNN is basically a neural network. It's just a different type of neural network. And why do we need an RNN is because it better holds information of sequential data much more better as compared to your multi-layer perceptrons or convolutional neural networks. So uh, if we go to the internals of RNN, so this is a structure or RNN in a sequence. For instance, here is a RNN block, here is RNN block, here is RNN block, here is RNN block, here is RNN block. So we need it for sequential data. Why? For instance, we are trying to predict what will be tomorrow's weather. So, for instance, we take tomorrow as t plus 1, today is t, and the previous day t minus 1, t minus 2, and so on and so forth. So in order to tell tomorrow's weather, we need to take today's weather in account as well as all the previous days' weathers. So we cannot just abruptly predict one random day's weather without taking into account the previous day's weathers. So hence we need RNN. CNN and multi-layer perceptron, they do not quite effectively hold previous information. So recurrent neural network, how recurrent neural networks actually hold previous information, it's totally in its internal structure. Here we have an example of the internal structure. I'll tell you everything what ct minus 1 and w dash w x xi f g ct all these are. So let me just use the pen. We'll use a red dot and no issues. So ct minus 1, oops, sorry. Yeah, so ct minus 1 is basically the output of previous cell state. In our case, it's yesterday. If we consider this as today, so this is yesterday. And we can see like we have two inputs and two outputs. This is an output and this is an input. So this is the output of the previous cell state that gets entered, or previous information as you can say, and this is the input of current cell state or current information. For instance, today it's 12 at noon and we were trying to forecast like what will the weather at night. So at 12 o'clock in the noon it's sunny, let's just say. So we are inputting sunny over here, and over here it was probably overcast. Yesterday it was overcast, so we will input overcast over here, just for instance. And this two gets merged over here. Here is a merge function. So what merge actually does, it basically concatenates. For example, what is concatenation? Suppose we concatenate A and B, so it becomes AB. And we shouldn't forget that these are actually neural inputs, and each and every neural input has a weight associated to it. So likewise we have a weight over here as well. We call it W for the current input, and for the previous input we call it W dash. So what exactly happens is the function generally becomes xiw plus ct minus 1 w dash. This particular area, sorry, this particular, after concatenation, this is what we get. So next what happens, we pass this output to a function like f. So f can be, like either a tanh function or a sigmoid or a relu, anything. So after inputting, the function computes itself and it generates an output. So after generating an output, we pass the output directly for the next cell state. I mean cell state ct plus 1 for t plus 1 time cell state. We need an input, right, like this one. So this is what gets passed to the next cell state. And if you want to classify here, right here, or a regression function, we either use a cross entropy or a softmax function, and we generate the output. And after we generate the output, we can either compute the loss function, or if it's a sequence, then for instance for here, if it's a sequence, then we can just compute in the last stages. So yep, this is how RNN basically functions. And so since this is your forward propagation, we are going here, 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 here. So in order to update the weights, we need to have some backward propagation as well. So we get an output over here, we compute the loss function, we get an output over here, we compute the loss function, we get an output over here, compute the loss function, loss function, loss function, if for individual cell states. And we combine all these loss functions and we generate the main loss function. During back propagation, the derivative generally works in this direction, from here to the loss, to the loss, to the output, to the output, to the cell state, to cell state, to the inputs. This is how back propagation actually works here. So there is a like a constant flow of gradient all throughout the network constantly. Hence RNN. For instance, where RNN is widely used for machine translation, um, weather forecast, then your stock exchange forecast. So for instance, my dog is a male, someone is trying to translate it to French. I don't know what French translation is. Just for instance, my gets inputted over here, dog gets inputted over here, likewise, like an encoder decoder basically. So yep, this is how RNN actually works. Am I missing anything? Nope, 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 nope. Yep, I said loss function concat. Yep, that is it, I believe. And yep, let's just take this example. We'll just erase this. Okay, let's just be. For the previous example, we considered O0 as CT minus 1. Let's just say CT minus 1 as O. So O gets passed to the first neural network, second neural network, and it gets passed, and again it gets forwarded, again it gets passed over input, again it gets forwarded. This is how it works. So here we are finally computing the loss function at the last neural network. So for computing the loss function, we use how loss function is computed. This is the loss. We compute a derivative of dl by dw double dash. So equals to d of loss by d of yi hat, then from yi hat to the weight, from yi hat to the weight. So dw my bad, dy hat to the dw double dash. Yep. So this one gets cancelled. Correct. Yep, this is how it works. Back propagation with time, continuous flow of gradients. Oh yeah, one more thing. Due to the continuous flow of gradients in the recurrent neural networks, we have to be very careful about two problems, that is exploding gradient problem or vanishing gradient problem. So what happens is, I'll tell you why this happens. Suppose in case of this particular function, we take this function as yep, we take that function as, let's just say sigmoid. So the value of sigmoid lies, the derivative of value of sigmoid lies between 0 and 1. So if our value is, suppose after consecutive a lot of multiplications of derivatives, our, if it is not 1, then it's less than 1. That means it can be 0 0.01, 0 0.9, 0 0.6, 0 0.7. So when we multiply this with this, when you multiply anything less than 1 with anything less than 1, it it becomes very minute. So with increasing number of multiplication, it becomes extremely minuscule and extremely tiny. Hence we have the vanishing gradient problem. And when do we encounter exploding gradient problem is how we like initialize the weights. If we initialize the weight as 2, sometimes 5, sometimes 10, then all this gets multiplied recurrent times and it just explodes a lot. The graph just keeps on increasing. So yeah, we do face vanishing gradient problem. There are tricks to go around this. For exploding gradient, we basically use what do we say, it's called identity matrix. We initialize the weight in terms of identity matrices. We initialize the in terms of identity matrices. And for vanishing gradient, we have some workarounds. Like instead of using tan h, we can just use relu, which is widely used currently. Yep, so this is how recurrent neural networks actually work. But we no longer use recurrent neural RNN in these days. We use some modified forms of RNN, that is LSTM and GRUs. I'll tell you why LSTM and GRUs are used and not RNN in the next session. Thank you so much.